Hello.
Hi, how are you?
Good. It looks just as messy behind me as it did before, but actually I've made progress.
Oh, good. That's great. Hello, Morgan, Susan.
Hello.
All right. So I don't know, updates, if anyone has them.
Updates. For me, not much. I've read the paper I told you about last week, and it's heavily into mechanical engineering math. And it doesn't do the compartmentalization of cells. It doesn't do that. It does where is the paper? Overall structure, but cells aren't necessarily connected in that way. So it's just doing material.
Okay.
So I don't know. I don't know how useful it is to me, for me.
Right.
And the one on tensegrity, I think I told you about it, and I don't know where it is might be useful for, it's useful for studying tensegrity of cells because it's looking at the elastic part of the cells or the strings being non-elastic, like it's for that end of things, and tensegrities, especially in living things, aren't elastic. Like they're not necessarily, they're as elastic as steel, for instance. So so that paper is useful for studying that end of things.
Yeah, that's good. So I know you sent those papers on tensegrity, and I was reading over them. And I have some slides, and I think I'm going to assemble a slideshow, and we'll go through it throughout the year. And we'll look at, like, some of the things, because you asked me, what are the mathematics?
Okay, I'm sorry about this.
Okay.
And try to bury it.
Okay.
There. I don't know. Can you hear it better or less?
Less, I guess. So, yeah, so you asked me about the mathematics of tensegrity, and, I guess I know some of the mathematics, but I want to go through and see what they're actually doing and, kind of the way it works.
Okay.
There's a lot of matrix algebra. There's a lot of sort of continuous dynamics, things like that. But I'm going to go through some of the things they talk about and some of the concepts. And then it looks like people use different mathematical tools to kind of try to solve or address some of these areas. So.
The title of this paper that I'm interested in is called A Modified Dynamic Relaxation Form Finding Method for General Tensegrity Structures with Inextensible Tensile Members.
Oh, that's a long title.
I'll put it in the chat. Just yeah.
All right. So that's good. Yeah, one of the things is form finding. One of the things they do in the literature. So I don't know if we had any other updates before we start. All right, why don't we get started? Oh, go ahead, Shreyas.
Yeah, just one question I had to ask. Just a second. Yeah, last meet I joined and we discussed that you suggested me to go through the Git repos and understand the codes for the last year's project of DevoTG. So yeah, I went through it. I had a bunch of questions. So I have put it on Slack to you in your DMs. So yeah, we will continue the discussion there, or can we so how do we work that out?
Actually, why don't I present this, and then afterwards you can go over your questions. I think that would be good to do it in the meeting.
Sure. Thank you.
Okay.
Sure. Yeah.
Yeah.
Okay. Thank you.
All right. You're welcome. All right. So let's start. All right. So, like I said, there's a lot of math you can use. Different papers use different math techniques for doing different things. And I'm going to add to this slideshow as we go and change things so that we have a slideshow of things that we know, kind of like a handbook maybe at the end. That's where I'm going with this. So one concept is constrained optimization. So as you can imagine, and we'll see this, tensegrity structures are quite complex, and you want to be able to optimize them for the properties of tensegrity. So you can generate a lot of different types of structures, but only a small subset of those are tensegrity structures, having all the properties that you would like. And you want to be able to optimize your structure for those properties, but you want to do that. You can't just do a brute force search. Obviously, we know that doesn't work particularly well. It's hard to find the things that you know are tensegrities or discover new tensegrities. And so this is an equation that they had in one of the papers. They proposed this simple equation, which is basically Fk over Ik, which gives you Qk, which is force density. So we're solving for force density. We have our individual forces, so that means that the individual components of the model are, we're going to account for each of these. We're going to sum them up or summarize them in some way, and we're going to minimize those in terms of force density. So we're minimizing our force density, and we're doing, we're using the individual forces of the components. But then we're also interested in the length of the components as well, or the length scale, or the size. And so there's Ik, which is length, or Lk, I guess, which is length. And then that proportion is force density. And so what we're doing here is we're optimizing an objective function while adhering to specific constraints. So there are a lot of ways to do optimization. You're using some sort of algorithm usually to enforce the constraints and find the optimal solutions. There are all sorts of algorithmic ways to do this, mathematical ways you can solve for this, and so forth. So there are numeric ways as well. So that's constrained optimization. And then there are some other things that we need to do to sort of get to that point of optimizing for these tensegrity structures. So I like this model that they introduced in this paper, Mathematics of Stable Tensegrity Structures. This is Harish et al. This is on the arXiv. And what they do is they talk about the mathematics of stable structures. So remember, optimal structures have the properties of tensegrities, but they also have to be stable. So you don't want to have something that is technically a tensegrity but isn't, stable either statically or dynamically. So, we obviously want a stable tensegrity structure that's static. I mean, we want to be able to have something that has these properties of superstability and so forth. But especially for biology, we want to have this dynamic structure. So if you're building a geodesic dome, that's a static tensegrity structure. It's just going to sit there and you're going to load it with things. And if you've ever seen the Epcot Center, or if you've ever seen these tensegrity domes that people built, and it's like a sphere, the top of a sphere with a bunch of triangular tilings on it. Then that's basically the structure, and these are super stable structures. Buckminster Fuller talked about them, classified them, etc. Those are static tensegrity structures. Dynamic tensegrity structures are going to be things that twist and bend. And those are the things that are interesting to biology, because In biology, of course, things are always twisting and bending and curving, and so that dynamic aspect is important. But this is a model that they use for static. I mean, they're not just static, they're also dynamic, but I think this simplifies it. This is called the Kite model of tensegrities. So this is a kite. If you've flown a kite, this is the basic structure of a kite. I mean, they have very complex kites, but like your basic kite is this thing that's like a diamond shape with an elongated bottom, and then they're cross bars, and those things then are parts of the tensegrity, and so they actually can take a kite and visualize the tensegrity, very simple tensegrity, and then classify the different components. So a kite model shows us that a tensegrity consists of B points in space. So the first thing we need are specific points in space. They don't need to be like specific to anything like in the environment. They just need to be there, have a relation to one another. So, we're not talking about a substrate. We're not talking about like anchoring the points in anything else. It's just kind of like a free-floating tensegrity structure. So a tensegrity consists of B points in space. And now they're going to start using notation. So we have notation of N rods. We have 2 rods. These are these double lines that go across. These are the crossbars. Now the notation is interesting because in different, even within this paper, they use different notation, and the notation gets a little sloppy with respect to consistency. So sometimes people refer to rods as R, sometimes N. Let me see. Am I right on this, or I think I have this legend backwards, but yeah, there are 2 rods, the double lines. That should be what I have for M should be N, and vice versa. We have 4 beads, which are B. So that's where we have the circles, the gray circles, and those are kind of the endpoints of each sort of directional dimension. So like, our edges are connected by these beads. If you think about a graph, those are the nodes of the graph. And N and M are the edges of the graph. So we can use a graph representation to represent this kite and characterize the graph statistics, and then, of course, expand this out to networks. So we can now build, not only more complex kites, but then we can move to the dynamic case, where where we can characterize the dynamics, we can characterize the translations. We'll talk about that in a little bit. But basically, that's the kind of thing we have. So we can use a graph model, or we can use this just basic characterization of the different components here. And so then we have M, or sometimes in the literature they call it C, which are the cables. There are 4 cables. Those are the single lines, and those are basically the topological configuration. So we're using, we're going in the direction of topology. So there's a whole mathematics of topology that if you dive in with both feet, you'll probably get lost. But if you think about this in terms of graphs, and then, of course, we know that we can use graphs to characterize topology. So, for example, in this kite, we have simplices, right? We have, if you're familiar with symplectic analysis or symplectic representations, we can build a graph, where you have diamonds, triangles, squares. So we have all these shapes embedded within this graph. And the idea is that we can characterize different nodes, or in this case beads, to say what the boundaries of that shape. So we have, how many triangles do we have in this shape? We have 4. We have a triangle, I don't have them labeled, but this bead, this bead, this bead, this bead, this bead, this bead, and we have 2 triangles on the other dimension. So we have 4 triangles, and we can just take those triangles out, and we can characterize the properties there as well. So there are a lot of things we can do with this mathematically. We can turn it into a sort of a set of simplices. We can have a standard graph. We can do a lot of things there. But the basic idea is we want a topology that's specific in space with spatial relations. So the way they define it here further is that the topology consists of the set R with unordered pairs, and this is where we're going to build a matrix of interactions between the I guess the beads, which would be ij. So we'd have unordered pairs ij. So again, in a graph, we have beads, which are the nodes. The nodes have connections, and unordered just means that you can go in either direction and characterize the interactions between I and j, ith element and jth element. So ith element and jth element, you could be interested in the relation in this direction or in this direction. We don't care. And so we have this pairwise relation, which is going to give us a matrix of these relations. And then once we have the matrix, we can do matrix algebra with that. So there are pairwise relations for rods and cables. And so we have these relations. We have the rods, which are these single lines, the cables, which are these double lines. And this is also important because we not only want to have points in space that are configured in space, but we want to be aware of length constraints, meaning that we don't want to have rods and cables of any old length, because if a structure is of a certain size, it might be a tensegrity, but if it's longer in one dimension or another, it might no longer be a tensegrity. So length is important here. If we can characterize the length of a tensegrity, as you can imagine, this kite, if this end, which is longer now, were infinitely longer, and it just continued on forever, it would be less stable in that direction than it otherwise would be. So that tensegrity breaks down. And so length is important, position is important, and the relations are important. The other thing that they talk about in the papers are these form finding methods. That's what Susan's paper of interest mentioned in that very long title, which was where they're doing dynamic form finding. Or there are all sorts of methods for form finding, and this comes from architecture. So this is a very interdisciplinary area. They do form finding in architecture. Like I said, when they build tensegrities in architecture, they want to be able to find the forms that are they're statically the most efficient, but also sometimes dynamically. Because remember, if you have a structure, it has to yield loads. It has to behave super stable with respect to wind and rain and all these other things, earthquakes that change might perturb the structure of the tensegrity. So the idea is that you want to find the best forms, especially when you have large tensegrity structures. And so they do this in architecture. They also do this in embodied robotics. And I have a reference, a couple of references by John Rieffel, who does a lot of work with evolutionary robotics and embodied robotics. So that there's form finding there as well.
This is origami, and it is related to tensegrity.
Yeah.
But it has a paper folding aspect to it.
Yeah. There's a hot area in like in nanotechnology and in embodied robotics. Like they're using origami and kirigami, and I think we talked about this before, where they're using these folding techniques to find structures, or they're using it to build more complex structures that just have like a flat surface and then they fold it up. So form finding, yeah, they use it not just for tensegrities, but they use it for other things as well. But the basic idea of form finding is where they have like a universe of forms, or like a latent space of forms. You might think of it that way, or like, we talk about fitness spaces. You could have a space of morphologies where you have all possible combinations, and then you try to search that space for the optimal structures, the optimal solutions. And that's form finding. And the idea behind form finding is very simple. You use an algorithm or you use some sort of constraint criterion to find the things that are most likely to give you the answer. You're approximating the answer from, this you're not using brute force search, you're using this very focused search. And so, what we want to do is we want to find the correct forms. And so we want to do this for static structures, but also for dynamic structures. So this is where we have to evaluate the forms not only statically, but like under rotation and translation as well. So that means that I can pick a structure that is maybe stable if it's static, meaning it doesn't change its configuration at all, or its orientation. And so if I find something that's a good tensegrity, it's static, that's great. But then if I rotate it, it's no longer super stable and so forth. So that's out. And then I find something that's both static and dynamic in its structure, then I can select that. So there's a lot that goes into tensegrity form findings, but other kinds of form findings as well. And there are different mathematical techniques, but they're doing here is just kind of characterizing this. So these different interaction matrices, these IJ matrices, so Rij and Cij, which are the end positions, can help us find an optimal distance between beads B. So basically, we have our beads in specific locations, and then we try different sort of end positions or lengths of the rods and the different connections between the beads. And so that's what we're doing here. We're just kind of looking at these, and of course, as you translate or rotate a shape, those lengths are going to change, the angles are going to change, and we can evaluate them with using these matrices. And so set R, which concludes all of these interactions, all of these IJ, so Rij and Cij would all be in set R, and that defines the static configurational space. So we want to be able to have the static configurational space and then search that configurational space. So if you're familiar, of course, with protein folding, you know that protein folding is an incredibly hard problem from a computational standpoint. You also know that AlphaFold has done a very good job of getting at that space and finding the optimal configurations for proteins. You know also that protein folding and what you might call form finding in proteomics this didn't just start with AlphaFold. They didn't just apply AlphaFold to the problem and solve it, more or less. They've used physics engines to do this for years and years, for decades even. And this is something, of course, that may be useful to tensegrities. It may not be useful to tensegrities because we're looking in terms of protein folding. We're kind of looking at the same problem. We're looking at the static structure. We're looking at the amino acid structure. We're looking at the topology, but we're also looking at the way they fold over time. And so we can, as long as we can simulate a long enough time course, and by long enough time course, we're talking about, maybe 1 or 2 milliseconds, which isn't very much time, but for a protein, that's enough to see how it folds and if it's like functional. We can then evaluate them. It's hard to say, tensegrities, how long do you need to simulate them to see how they behave under translation rotation? It might be quite a long time. In biological terms, of course, a long time it could be a millisecond. It could be maybe years. We don't know what the time course is for this. So, we can apply computational methods to this and look at the dynamics, but it's hard. And it's even hard to do this with static structures because if the structures are sufficiently complex if they have enough beads. I've just given you the 4 beads, but if we had 4,000 beads, then that's also another bigger problem. So again, when we talk about static, we're talking about the position. Position is more or less stable, but the length of the rods and everything vary. And then when we talk about dynamic, we talk about translation. So we're rotating the structure, we're rotating, maybe we're moving the beads into different positions as the thing moves. We want to characterize this continuous movement. So in the dynamic case, configurational space is reduced more by considering only those things that are stable under rotation. So what we're doing with the dynamic aspect of this is not just saying we only care about those things that are stable dynamically. It also helps us to winnow down that list of probable stable structures. And again, we don't know what structures are stable until we actually test them experimentally or build a model. So we don't know that from just the search, but it helps us to winnow down those possibilities because it's a very large space, as with proteins. So that's what we're doing there. We're just applying more and more constraints to find a smaller set of solutions. And then our design tensegrities employ methods that lead to string-deficient structures. So another thing we want to do is we want to be able to simulate these things, not just in terms of their basic structure and their rotation, but we want to find other types of properties where we have soft swinging modes. We want to find some of the properties like the lack of rigidity, and those are things that we can't just apply engineering tools to. We maybe need to have new tools, or we need to use new methods to find those. So I wasn't, and I haven't gone through the papers yet, but I wasn't clear on if there were any really good methods that people have identified. And I think the point here is that there are no really good established methods of doing this. So it's kind of an open problem almost. These things exist. You can use different methods, but there's no really good method for it. So it's hard to say what would be the best method. Okay. So this is a paper, and this is where, this is from this field of embodied robotics. This is not, it's a computational technique. So I'm not going to talk about any math here. There's math underlying this, but the idea is we're going to do form finding, topological form finding, which is nominally static. This is this paper, Hermann et al., Basic Investigations on a Compliant 2D Tensegrity Grid for the use in soft robotic applications. This is where they have these grids, these tensegrity grids, where they're going to do form finding by drawing different structures within each cell of this grid, and they're going to compare the different structures. So the red lines here are the segments of the compressed members. The thin black lines are tension members, and then the gray marked areas, these cells that are gray, are elementary tensegrity cells. So if you see this, and I didn't dig deep enough in this paper to really understand it intimately, so I'm probably missing things here, but basically this grid is the whole tensegrity structure. You have these red lines, which are the compression, they behave under compression. The thin black lines between are the tension elements, and then the gray marked regions, these different cells that are gray, are the elementary tensegrity cells. I guess that means they're the stable tensegrity structures of the lot. So we have various polygons arranged in a variety of patterns that can be used as basic geometries or fully filled 2D grids with edge-to-edge tessellations. We have these tessellations across the grid, which means they're just different ways of configuring these lines, these red lines. And so you see that there are different strategies here. Some of them, the red lines, the compression lines kind of go up to the corners. In some cases, they kind of branch off before the corners, and they have contact with the compression or the tensioned members out on the edge. And there are different configurations that we can test this way. So we can test all sorts of different configurations, and we can get a handle on the geometry much better. But this is, again, topology. This is, there's a whole mathematics of tilings and things like that. And that's relevant.
They need to be hexagon tiles.
I didn't see it in the paper, but yeah, I mean, that's like kind of the basic thing, right? The hexagons. But yeah, I didn't really dive into this paper. They have a couple of papers from this group where they're doing different methods. So they might have them there. Okay. So this is like, this is where they have different types of these tilings and they're classifying them. So they have 6S, 8DS, 8S, 4D, 2S, and 8S, 4D. And this is where we have D and S stand for. S stands for side centers, and D stands for diagonal corner points. So diagonal corner points is where you have a point that hits the diagonal and the diagonal corner, and then the side centers are points that hit the sides, and you can differentiate between those. And you have different motifs that you can characterize using this method. So there are different tilings, and there's a whole mathematics of tilings, and it's related to topology. And basically, we're trying to find the optimal topology here. Now, in embodied robotics, they want to build these super stable soft robots. So, you have soft robotics where you want to have compliant materials, but you also want to make the body super stable. And that is actually a nice connection to biology, because in cells, you also have this imperative that you want to optimize for these compliant materials. I mean, the membrane is pretty compliant. Different components of the membrane of different things going on in the cell, but also you want them to be super stable, especially when you have sheets of cells. And those sheets also need to be pretty stable, and they need to be able to change their shape and change their orientation with respect to cell migration and repair of the sheet and things like that, which is also something that they're interested in biorobotics, is this ability to repair, for the robot to repair itself. I mean, they don't call the sort of the body of the robot a skin, but basically that's what they're aiming for. So it's definitely a place to look for mathematical models and for techniques, because they're kind of going in the same direction, I think. Although I don't know if their mathematics are kind of suitable for cell biology. They may have specific imperatives to robotics that they sort of have there. Okay, so this is a little bit more about the math here. So when we talk about dynamic structures, we consider a matrix of positions P. That's matrix IJ. Any kind of IJ relationship is a matrix. We have matrix of positions, and those positions are, characterize a static shape or a static tensegrity structure or a candidate tensegrity structure. And what we're going to do is we're going to perturb those structures with a motion T. So if we have our matrix of positions, we perturb it with a specific external motion. Say we smack it with a hammer, or we kind of shift it, in some way. We introduce like water flow or something, liquid flows. Then we have motion T, which produces a new configuration P prime. So basically, we have this matrix of positions P. We introduce this perturbation, motion T, and that produces a new configuration P prime, where maybe some of the positions are displaced. So the sort of the point is that if P equals P prime, or sometimes you could say equivalent, which is if you add another bar to this symbol, if P is equivalent to P prime or P is equal to P prime, basically if there's no effect of the motion, or if the effect of the motion is basically turns the P prime into an equivalent topology. So under rotation, you have things that are basically equivalent if they move. So you might have like the kite that rotates 90 degrees. It's still, the points are not in the same position, but they have the same relationship to one another. If that equality holds, then we have these soft modes, and the soft modes relate to null eigenvectors in the matrix. So we're going to be taking eigenvectors from this matrix, and we're going to be evaluating them. So basically, if you take them, I'll show you a graphic of this, but if you take different slices out of this matrix, you can characterize those using eigenvectors. Those eigenvectors can tell you things about the dynamics of the structure that are, informative to the mechanics. Now, if P is not equivalent to P prime, or not equal to P prime, then changes require a new shape to be stable. So basically, when we perturb P, we're getting P prime, and we have to evaluate P prime. If P prime is equal to P in terms of its stability, then you have these soft modes, which means that you have the new modes that open up and preserve the sort of the structural stability. If P does not equal P prime in terms of its properties, then you need a whole new shape to be stable. Basically, it breaks the structure and it collapses. So that's how they're thinking about this. Now, in three-dimensional space, a structure will collapse unless anchored at fixed points. And we have these different load, we don't want to work in high-dimensional space because it's very hard to solve these things. We want to have low-dimensional examples to demonstrate the calculations. That can also apply to freestanding stable tensegrities.
Tensegrities will also change shape dramatically.
Yeah.
So they won't necessarily collapse, they'll just simply change shape.
Okay. Now, this is like if it's a stable tensegrity or if it's like just responding to forces. Like, I guess the point here is that, and I don't know if the language is correct on this, but like, you can have, a drastic change in shape and still be stable, or do you have a drastic change in shape that makes it basically non-functional, but that's what the result of the forcing is. Is that clear? Yeah, anyways, I don't, yeah, so, yeah, I may have to dig more into that and see what they're...
I have an example, well, that I found for my thesis of something that was sort of basically round and then collapsed into kind of a bowl shape.
Okay.
So there are examples, and there's, yeah, I think Dick had a bunch of them too.
Okay.
He was fascinated by them, so he has some examples.
So in biological terms, if we had a sphere that collapsed into a bowl, would that still be considered like a stable structure, or would that just be like, I'm using the term collapse kind of colloquially here, but like, would that be considered the same? Would that be considered a function, or is that like just kind of...
That could be a function. That could be useful in a biological system.
Yeah. All right. I'm just taking some notes.
Yeah. Well, then it has two forms that are essentially stable, and it'll switch between the two.
So we have bistability, basically.
Yeah. Mm-hmm.
Yeah, that's good. So yeah, that's that's a little bit about like how they think about these kind of changes. So this is I was talking about with eigenvectors. So you have these force vectors in the matrix. You have these components that are interacting, and you have, basically it's a force calculation where you're minimizing these numbers. You're also able to get eigenvectors, which describe the modes. So you can have force vectors which are either 0 or non-zero. And, it's just different sort of orientations of the matrix. So you might have something that's like a diagonal, or you might have something that is up or down, like vertical or horizontal across the matrix. And those are the force vectors. And so it's just describing different orientations of forces throughout the structure, and we can calculate the forces for that. And then we can say things about the structure. And so you can see that you have a lot of potential force vectors in here, right? A lot of different ways to describe forces on that structure. So that, in the larger the matrices, the more force vectors you have. And then, optimizing those to 0 or non-zero is a harder problem. The last slide I want to talk about are these indeterminacies. So tensegrities are indeterminate, and as Susan's discovered, that makes it hard to simulate in, say, like a standard multiphysics software. And so this is just the property of tensegrities. You have static and kinematic indeterminacies. So static indeterminacies are these membrane reaction forces that are subject to external nodes that cannot be uniquely determined. And static indeterminacies are related to pre-stresses or allow for pre-stresses. Whereas kinematic indeterminacies, again, static is where you have the static shape, and you have these indeterminacies in that. Then you have kinematic indeterminacies, which are when the thing is under translation and rotation. And this is where we have nodal motion that keeps lengths of all equivalent edges the same. And then this allows for movement around axes, so this allows for translation. So that's as far as I've gotten into this, and I know that this doesn't cover, yeah.
Sorry, I have a table about the static and kinematic indeterminate status, and it has to do with how many rods are connected to each other.
Okay.
So I have a table.
Okay, your thesis.
I'll get it to you. It's Gann's book on tensegrities. And in living systems, you will get two rods connected to each other, like two, microtubule structures connected to each other. So it's probably indeterminate, both kinetically and dynamically indeterminate, kinematically indeterminate. Yes. Try to use the same language. Yeah. Anyways, kind of unstable, but work really well for biological systems.
Yeah. So it's stability versus, or not versus, but it's stability and or function. So it's like,
well,
yeah.
okay.
So it's like function.
That's where I was. That's when That's when I was explaining that if you have two rods connected together, they act as a double pendulum. And if you swing a double pendulum, it's a chaotic system.
Oh, right. Yeah.
So therefore it's indeterminate. That's where that comes in.
Yeah. Of course, there's the whole mathematics of chaos, which actually I should bring up a little bit, because that's like kind of maybe relevant here.
Yeah. So they want me to use structural engineering to figure out a chaotic system.
Well, yeah.
Well, this is why I was having trouble. It's like there's a, what is it? If you're a mechanical engineer, if it's if it doesn't move, it's broken. If you're a structural engineer or a civil engineer, if it moves, it's broken. So I have a structure that moves. So I'm in trouble. It's kind of obvious.
That's good.
Yeah. And it takes an electrical to get wound up in such a ridiculous system. Mm-hmm. Yeah, that's what.
Multiphysics, yeah. That's
Anyway, yeah.
all right. Well, that's good. All right. So that's. Do you have anything more to add, Susan, on papers?
Well, there's a K factor that you need to look into, and it's not the one that GAN shows. There's different K factors. Anyway, the K factor that is the difference between the elasticity and area of the cables and the elasticity and area of the rods is an important factor. Because I can adjust my model to different materials depending on the difference between those, the elasticity of those two things. So I was able to match skin, and I was able to match single cells that came from heart material by adjusting that K factor. So that was very important. It's not immediately obvious by reading the literature. Yeah, that was very intriguing.
Yeah. All right. So yeah, I think that's enough for that. I did want to give Shreyas time to talk about the things on the repo.
Oh, could you send me the slides? Maybe I could add a couple of slides to it, or we'll do a.
Yeah, that'd be good.
Yeah.
I'll send it to you. Link.
Because you've covered different things than I did, so.
Yeah. It's just kind of like that's what I want to add, or I want to like keep adding to it and kind of figuring out where the.
Yeah.
Shreyas, are you there?
Yeah, I am there.
Yeah, well, you can go ahead and if you want to share your screen or whatever you want to do.
I just wrote some like text, like what doubts I had. I didn't like do any coding experiments as such. Like I had some mathematical doubts as to what we can do. So I basically went to the DevoTG repository, which was a project for last year, and I understood what we are doing. So basically, what I understood is that there's this worm called C. elegans, through which we have its data for lineage and connectome. So we are predicting the links in the future links in the lineage by modeling it as a temporal graph, which is like real-time graph changing, like new nodes are added. So that's what I understood, and I understood like how is the message computation done, like time encoding done, GRU-based memory modeling, and graph attention layer. Yeah. So my questions were that the first question is that we were the graph attention layer which is being used is basically using a top of the shelf PyTorch layer. Like there's a PyTorch module which has attention layers in it. So like transformer conv, to be specific, we are using that. So is that the most optimal way to do it? Can be like the way physics inspired neural networks are there. Like say they encode some physics in the network, say like energy is constant, like it can't change. So can we also do some custom attention layer in which we encode some biology, like some basic rules of biology in it, through which we can get a better output? Like what are your views on this? Like I'm not that well aware about things, so I just thought that can this be one of the options to do in future maybe?
Yeah, I think so. Like, we're just kind of talking about that, where you have to have, specific or specific things that you discover about the system, and so like I think we can definitely customize the attention layer, and there are a lot of things that, like if we want to be very specific to what's happening in C. elegans development, because the lineage tree is not a full description. It just tells you how cells divide and maybe what their location is in like the anterior posterior axis. And we have
Right.
positional data, but we don't, we're not describing everything. We could describe other aspects of development, in the lineage tree, what's going on there. So yeah, we could do that. We could customize it with, different components. It could be like, molecular biology. It could be the physics of the embryo, things like that. I'm not sure how Jayadratha defined everything in the attention layer. So, I mean, that, like, I guess best way to do that is to kind of point out what's going on there and like how you plan to modify it.
Right.
How that would improve prediction, perhaps.
Okay, one just naive thing which I came across on the internet, like please let me correct me in the biology part because I'm just learning it, is that let's say there is an embryo. As of now, the like what it does is like it like for the biology part which I'm asking, the negative sampling. The negative sampling is random. Like for the parts which are not a parent-daughter link, they are just randomly sampling and taking anything. But what I encountered is like say there are two cells, there is an embryo in which organs are going to develop from. So like cells are going to divide and get into some organs. Now say some cell is near the gut, like it's supposed to be the gut, and whereas some other cell is in the other end of embryo, which is supposed to be some other type of organ. So say cell A and cell B, we have two, like cell A and cell B. So like cell A cannot give birth in the later stage to cell B because it's in the other stage and it's supposed to be some other type of organ. But whereas in negative sampling, what we are doing is that we're just randomly selecting. We are not getting hard negatives. So what I thought is like this is making it easier for the model to get a good accuracy, because if say it learns that the farther the coordinate is, the more unlikely it is to be like one cell to be linked to another. So like, is this a thing, and can we like somehow like get some harder negatives and make model to learn some more niche biology stuff rather than just learning that okay, if it is far, then just like don't link it and making the accuracy higher. Like this is what I think, that this thing is making accuracy higher because we are getting like easier negatives are being constructed and some harder negatives can be constructed is what I'm thinking. What are your views on this?
Yeah, so that's good, I think. So in graph theory, we usually use random graphs to describe kind of like the null condition. And then, we usually have structured graphs that we compare it to. So, I mean, definitely we want to be able to account for structure. Like in the early embryo, there isn't a lot of structure, so it doesn't necessarily help. But eventually you can improve the model, I think, by doing that. Now, this is, again, how are we going to introduce that constraint with the data that we have? And there are a couple ways you can do that. One is by looking at sort of the relative position of the cell. Like, so if it's in a place that we expect muscle, we might introduce a constraint for that. If it's in a place that is like if you look down the lineage tree, eventually these things differentiate. There's certain sublineages that yield certain types of cells, like the C lineage and the D lineage. They're very specific, but the AB lineage, of course, is more general. But we know that, like, if you get down in terms of granularity, that certain parts of the lineage tree are going to yield certain cells. So we have those constraints kind of built in, at least in terms of C. elegans biology, as to what things are going to happen.
For vertebrates, don't forget the neural crest cells, because they move. Yeah. They're mesenchyme, they're crawling cells, and they'll move the whole length of the backbone. So you have to watch out for those in a vertebrate.
Yeah.
They will. They really do move.
Yeah. So there are all sorts of constraints we can introduce. I think in C. elegans, I think it's probably the easiest way is to look at the lineage tree and kind of think about, or maybe the positions of the cells, and kind of think about which we should expect for those places. It would have to talk about that more, because we'd have to kind of come up with a scheme for it. And then Susan's talking about, like, if you were to apply this to, like, vertebrate systems where you have like different germ layers, and then you have like different things going on that emerge from those germ layers, and there's all sorts of migration and formation of structures. And so there's, in C. elegans you get structures, but those structures are more deterministic in the sense that we know kind of what the cells are going to become. But it's like, what is, and I don't think people know exactly what happens in the regions where you get these cells. I guess because they're deterministic, it doesn't matter so much, but you can perturb the system in different ways and like get things that are non-functional. So it's interesting, and I don't want to get too deep into the biology here, but we can deal with those we can kind of come up with a scheme that deals with that, and that would make, I think, the TG approach much more interesting.
Right, yeah, understand. And yeah, one more doubt I had is that I see that the edges, one of the part of the edges were the exact coordinates, like the XYZ coordinates of the parent cell was one of the parameters which was being inputted. But then it occurred to me that what if, like, is this rotation invariant? Like, say the embryo rotates by 70 degrees, 90 degrees, but we are not inputting relative distances, but rather we are inputting exact coordinates. So does inputting exact coordinates not make it like rotation variant? Like, what if the embryo does shifts and all, right? So how can we make it rotation invariant, and is it actually useful to make it rotation invariant? Is it an issue?
So a word about like where the data come from. So it comes from cell tracking data. So like when they collect the data from a microscopy example, they'll have like a sort of a coordinate system. They'll track the cells. The cells are a certain distance from one another, or they're in a certain position in the slide. And the data sets that we have to work from usually get normalized in some way. So you normalize the thing to the center point, and you kind of average out over a bunch of observations, and you get a number, which is somewhat useful. If you construct a point cloud, you can see where the points are. So there are advantages and disadvantages to that, one of which is it doesn't really do a very good job of accounting for cell migration. In C. elegans, that's not such a big deal because there's always this sort of a similar place where the cells end up. So if you were in a system where you had, like in a mammalian system, that might not be so useful because you have cells that migrate and are subject to signals, like regulative signals, that mean that if you're it's not a deterministic position. So that's a thing that we kind of a best way to do it sort of thing that we've come up with. Now, in terms of rotating it, it's rotation invariant. I guess in the sense that, you can, I don't know how to answer that. But yeah, it's like, you mean it preserves the structure as you rotate the points? Is that what you're getting at? Or, what were you thinking about in terms of, what did you want to do with the model, I guess?
Yeah, so like basically my thought was that the same only, like what if, like, say later data, whichever data we get, like say which we want to predict, like actually use model somewhere, and what if like that the coordinates exact which we are implementing that are not the way we expect it to be centered.
Right.
Yeah, so like would it affect the results?
Yeah, it probably would. I'm not really sure though what the answer is there.
Cool.
Yeah, is you'd have to play around and see what you get.
Right. Okay, and one last thing, like this all prediction was for lineage prediction. For connectome, like I understood that we were doing the visualizations using the DevoGraph library. The various types of visualization and analysis was done for lineage and connectome. So prediction was done only for lineage part. So is there any like can we do any prediction for connectome part as well? And like what can we do there? Is there any avenue?
Well, we have the lineage tree. We know what cells are going to become neurons, so we can trace through the lineage tree find the endpoints. The cells are neurons, and then we have those positions just kind of by default. We don't. I mean, the connectome data is a little bit different in that it's like, we're looking at the connections between cells in different ways. There are different types of connectome, but yeah, we can combine the lineage tree and the connectome. We've done that before. We have some papers on that, but there are different ways you can do that too, because it's interesting how those things kind of emerge as the cells differentiate. They'll form connections, or they'll kind of be in place, and so we can talk about that more. But suffice it to say, there are connections there we can use, but I'm not really sure. Again, we'd have to decide what's interesting there.
Yeah, sure.
Yeah.
Okay, yeah. Thanks for giving time. One last thing I had to ask, what would you recommend me for next week to read up, and what should I go into, and what should I read up to understand more about this topic, and what are the aims for this year, so that I'll be well aligned with the aims.
Yeah. So Jayadratha and I are working on a paper on this, so
Okay.
I can share it with you. I guess the current state, and then we have some other things that we're doing. I guess one of the aims is to improve upon the model. So we got to a certain stopping point last year, and we're going to keep improving it. And I guess Jayadratha has created some issues, hopefully, in the repository. You could look at those. You could also get in touch with Jayadratha. That's what people usually do.
Will I find him on the Slack channel?
I think he's in the Slack, or he might not be in the OpenWork Slack, if I recall, because he couldn't get in. But I'll put you in touch with him.
Sure. Yeah. Okay, cool. Yeah, let me know. Put in touch. I'll also look into this and excited to work on this thing.
Yeah,
this year.
Sounds great. Yeah, I'm glad to hear you're enthusiastic.
Yeah. Thank you for your time.
Yeah, you're welcome.
Yeah.
Susan, you wanted to say something?
Yeah, I look forward to adding a couple of slides to what you've made there. Because I have them already prepared, or they were part of my thesis. So.
Oh, that's great. Yeah.
So I could just add a couple of slides that go with the instabilities.
Okay, that's great.
Maybe I should explain the double pendulum too while I'm at it.
Yeah, that'd be good.
Yeah.
Yeah. All right. That's great. So I think we're done for today. So have a good week, and talk to you next week.
Yeah. Thank you.
Okay.
Thank you.
Bye.
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 So one thing I mentioned in the tensegrity slides is that tensegrities are useful for soft robotic design and in the field of soft robotics more generally. And so this is one of the papers that they had. It was, I guess, a review article in the journal Soft Robotics from 2018. And this is an article called Adaptive and Resilient Soft Tensegrity Robots. So this is from John Rieffel and Jean-Baptiste Mouret. They talk a little bit about how they apply tensegrities to these kind of soft robots, which are adaptive and resilient. So the abstract reads, living organisms intertwine soft and hard materials. So soft biological materials are muscle, hard biological materials are bone. And of course, you're intertwining them into systems. So muscle is over bone, and it enables both rigidity and movement. This gives living organisms an intrinsic flexibility and resiliency, often lacking in conventional rigid robots. And so the emerging field of soft robotics seeks to harness these same properties to create resilient machines. The nature of soft materials, however, presents considerable challenges to aspects of design, construction, and control. And up until now, the vast majority of gates for soft robotics have been hand designed through empirical trial and error. So the whole idea of soft robotics is we want to create these structures that are maybe more biological. We want to understand the design principles behind building these things, which of course it could be that, you may need to use an evolutionary approach to sort of build structures, much like biology does, or you could figure out kind of key aspects of stability and the structural stability and structural relations between these components that, are sort of optimal, but also flexible enough to operate in different modes. So what they're going to be doing is they're going to be thinking about optimization, but they're also thinking about the sort of form finding. This article describes an easy-to-assemble tensegrity-based soft robot capable of highly dynamic locomotive gaits and demonstrating structural and behavioral resilience in the face of physical damage. Enabling this is the use of a machine learning algorithm able to discover effective gaits with a minimal number of physical trials. So they want to be able to get something that can walk quickly. You don't want to have to train it very much. You also want something that is structural and behaviorally resilient. So you want something that can walk under a wide variety of conditions, something that can be structurally stable under the same kinds of conditions. These results lend further credence to soft robotic approaches that seek to harness the interaction of complex material dynamics to generate a wealth of dynamic behaviors. Okay, so this basic problem of machines not being like animals in terms of how they can exhibit resilience. So this is a common problem, I think, with artificial systems or machine systems, is that they just don't have the sort of resilience and variety that living systems do. In nature, the suppleness, and they define suppleness as sort of the combination of soft tissues and rigid skeletons. This suppleness leads to several compelling behaviors that exploit the dynamics of soft systems. Octopi are famous for this muscular hydrostat, which is where they have an arm that consists of muscle ganglia. And each of the muscle ganglia are controlled independently, so they have a large number of degrees of freedom so that arm can grasp things, it can wrap around things and manipulate them. It's a very different mode from what we do as humans in terms of reaching and grasping. And it has a very similar function, but it's very different in terms of its structure. And so they're able to perform these adaptive behaviors with this soft-bodied mechanical system. Jellyfish exploit their inherent elasticity to passively recover energy during swimming. Manduca sexta, which is a moth, which has a caterpillar life history phase, have a midgut which acts like a visceral locomotory piston. So we can actually take some of the structures in biology and characterize them as these machines. In this case, the midgut acts like a visceral locomotory piston, sliding forward ahead of the surrounding soft tissues, shifting the animal center of mass forward well before any visible exterior change. And this is the way this caterpillar moves. So they move their mid-body forward and the rest of their body follows. And that's their form of locomotion during this period of their life history. Taking inspiration from the natural world, the field of soft robotics seeks to address some of the constraints in conventional rigid robots through the use of compliant, flexible, and elastic materials. So compliant materials are things that give in response to forces. They don't shatter, they don't kind of lose their function, they kind of blend in with the forces of the world. They're flexible, they're elastic. Trimmer, for instance, constructs soft robots from silicon rubber, which is a sort of a compliant material, using shape memory alloy microcoil actuation, which can slowly crawl in a controlled manner or roll in an uncontrolled ballistic manner. So they have different types of behaviors, slow movements that are more controlled, or rolling that's more uncontrolled. Similarly, research by Whitesides et al. Used pneumatic inflation to produce slow, dynamically stable crawling motions as well as fast but less controlled tentacle-like grippers, combustion-driven jumpers, and self-contained microfluidic octobots. Despite their advantages, soft material robots are difficult to control by conventional means. They are by their very nature high-dimensional dynamic systems with an essentially infinite number of degrees of freedom. The elasticity and deformability that provide their appeal come at the cost of resonances and tight dynamic coupling between components. Properties that are often avoided or at least suppressed in conventional engineering approaches to robotic design. This complexity precludes the use of many of the traditional kinematic and inverse dynamics approaches to robotic control. Up until now, the locomotive gates of most soft robots have been developed by hand through empirical trial and error. This process can be both challenging and time-consuming, particularly when seeking to fully exploit the dynamical complexity of soft mechanisms. So this is where they introduced tensegrities. Tensegrities are relatively simple mechanical systems consisting of a number of rigid elements, which they call struts, joined at their endpoints by tensile elements, which are these cables or springs, and kept stable through the synergistic interplay of pre-stress forces. So they get into this in figure 1. We'll look at that in a minute. Beyond engineering, properties of tensegrity have been demonstrated at all scales of the natural world, ranging from the networks in the human hand to the mechanotransduction of living cells. And then, so at every size, tensegrity structures exhibit two interesting features. The first is they have an impressive strength to weight ratio, and they are structurally robust and stable in the face of deformation. So the first is that they have this impressive strength to weight ratio. So it means that you can stress them with a lot, and very lightweight structures have a very large ability to be loaded and to be stable under that load. And then we have these structural robust and stable structures that are basically invariant in the face of deformation. So you can deform something quite a bit and they respond by maintaining their shape. You can also load them quite a bit and they are still functional. So this speaks to biological function, that we want structures that maintain their function under these conditions. Moreover, unlike many other soft robots, tensegrity structures are inherently modular, consisting of only struts and springs, and they are therefore relatively easy to construct. They are simple enough to be baby toys and featured in books for children's activities, whereas complex enough to serve as a basis for the next generation of NASA's planetary rovers. The most common control method for tensegrity robots, then, is to slowly change the lengths of the struts and their cables, causing large-scale quasi-static rather than dynamic structural deformations, which in turn make the robot move through its tumbling and rolling. So they basically use sort of perturbations to move the robot. So they're able to do these different modes of movement. They can do these uncontrolled movements or these controlled movements. And I find it interesting that they kind of focus on this, because this is something that we often use in other types of robotics. We often use neural control, or we often assume that neural control is necessary for it. And one of the lessons from embodied robotics is that the body actually plays a role in some of that control as well. And that's what we see here. We have this body-shaped control, that basically the body is responding to what are essentially stochastic perturbations, and it's producing these behavioral modes, which are, actually get the job done, basically. And so this is a soft tensegrity robot. They have some figures here where they show tensegrity structures, and then they show their robot that they've built. So in A, we have this mechanical structure, which is purely mechanical. There's no soft aspect to this, no biological aspect. These are bridge constructions. So this is one aspect of a tensegrity arch. This is another aspect of a tensegrity structure in bridge building, where they have to maintain loads. and they and as well as stability under environmental forces like wind and maybe even being struck by something. C is where you see tensegrities in biology. C specifically is mechanotransduction in living cells. So you have these forces that are transduced into the cell from other cells around it, and the cells respond in kind. And then, of course, we have our robots that they have here. So D is a robot that's based on carbon struts and springs, actuated by 3 vibrators, glued to 3 of the struts. Its frequency is automatically tuned by a trial and error learning algorithm. So there is some neural control in this, but it's tuned. It's not generated de novo by the algorithm. And then E is, thanks to the tensegrity structure and to the compliance of the springs, our robot will keep its integrity when deformed and spring back to its initial form. So here you see that this robot, if you push it with some stochastic perturbation, it can move in these different modes. You can tune that mode through some sort of neural control. But then, of course, the idea is that you can deform the thing severely and it'll pop back to its original shape. So it always remembers its old shape. It has this sort of morphological memory. And then, of course, it's able to still produce behaviors that are produced by the morphology. So one of the things about this paper is they talk a little bit about dynamical methods of tensegrity robot control. So that relates to the things we were talking about with dynamical modes in tensegrity structures more generally. So researchers have begun investigating this. Bliss et al. Have used central pattern generators, or CPGs, to produce resonant entrainment of simulated non-mobile tensegrity structures. So CPGs are like these oscillators that are produced. If you look at insect gait or insect movement, where they have a bunch of legs and they're centered upon a bunch of bundle of neurons in their midline. In their notochord, they have these different neurons that produce networks of neurons that produce oscillations locally. They drive the legs, and that drives movement. So you can use central pattern generators in very interesting ways to produce movement behaviors. And if you have a bunch of central pattern generators arrayed across like a notochord like you have in insects, you can entrain those central pattern generators to produce pattern movement. So insects will walk forward or walk backwards, and this depends on sort of the way in which the oscillation is being produced in the single central pattern generator, and then how those central pattern generators for each pair of legs are entrained. So there's very interesting things you can do with stochastic or quasi-stochastic systems with respect to bodies, especially with tensegrity structures. Mouret et al. Have used CPGs to produce goal-directed behavior in simulated tensegrity spine-based robots. These efforts, however valuable, were all produced in simulated environments, so we need to have real-world robotic examples. As Mouret's point out, the dynamic behavior of tensegrities is highly dependent upon the substrate they interact with. So this substrate, and this is the same thing in cellular systems. If we talk about our cell sheet, our sheet of epithelial cells, we have a substrate which the cells adhere to, and that substrate affects the behavior because, as we talked about, these tensegrity systems have to be anchored on a substrate in order to be to exhibit a lot of these tensegrities in the first place. In this case, we have different substrates that are where these robots can function, and so depending on that substrate is going to give you a certain mode of dynamics. So we can't necessarily assume that something we produce in Simula will transfer to the real world. So this is, of course, in evolutionary robotics, this is known as the reality gap. More recently, Bohm and Zimmerman developed a tensegrity-inspired robot actuated by a single oscillating electromagnet. And so this was compellingly able to change between forward and backward locomotion by changing the frequency of the oscillator. Vibration has been proposed as a means of controlling much softer robots as well. So they not only need to find the tensegrities, the right shapes, but they also need to find the right vibrational frequencies to produce some of these behaviors. They were trying to do this kind of form finding and behavior finding. And again, this is a hard problem that involves a lot of, could involve a lot of computational power, but, we want to be able to add constraints and find the right answer for our system. So in this case, what they describe is this improvement upon earlier time-intensive methods by employing a Bayesian optimization algorithm, which allows us to find the maximum of a performance function with as few trials as possible. So they're training this tensegrity structure to do these different behaviors. They want to find something that's very efficient in terms of learning, or at least in terms of getting coordinated on its substrate. And so what's interesting about Bayesian optimization as opposed to some other form of optimization, probabilistic optimization, for example, is that Bayesian optimization starts with a constant prior for the expected observation. So we usually have a prior, which is a distribution of maybe, like in this case, an expected speed. And we use that prior to sort of figure out, if we observe a bunch of different variants, which of those variants match our prior. And then we can have a posterior evaluation of that observation that lead to updating the prior, and we can run through that space and eventually find the optimal solutions to the problem. And so we have different ways we can initialize the model. We have a few randomly chosen trials. They say for this robot, however, common sense along with preliminary modeling suggests that speeds near the motor maximums are more likely to produce successful gaits, and then near zero motor speeds are not expected to make the robot move. This insight was substantiated in preliminary experiments. Many effective gaits were produced by high motor speeds, both forwards and backwards. Therefore, to speed up learning, we use a nonlinear prior model that includes the following points. Number one is that if the three motor speeds are close to zero, then we should expect a locomotion speed close to zero. And then two, if all the motors are close to full speed in any direction, then we should expect the maximum locomotion speed. And so we don't need to seed our algorithm with any random sample points. We can, start with our prior and work from there in Bayesian optimization. So that was sort of thinking about the control policy for movement. But of course, as we go back to this idea of form finding, we're basically trying to search through a very large search space to find optimal solutions. So some of that has to do with, kind of having the right algorithm, having the right criterion, but some of this also is where to get to this behavioral policy, we need to address the design of the structure. And so there's some initial form finding that happens before we move to defining the control policy. In this case, we purposely designed the robot so that the search space is as small as possible, which in turn makes it more likely for the robot to be able to adapt in a few trials. Put differently, one of the main strengths of vibration-based locomotion is to make the search problem as simple as possible. Although in principle, a variety of optimization techniques, such as simulating annealing, might be used, there are compelling reasons why our adaptation algorithm is based on Bayesian optimization. A couple of those reasons involve it is a principled approach to optimize an unknown cost-reward function when only a few dozen samples are possible. And if we wanted to use simulated annealing, we would need to have the statistical properties of the search space where we can actually operate from a large number of samples and define So, in cases where you don't necessarily know the statistics of your search space, you can use something like Bayesian optimization over some other alternative like simulated annealing. 2, it can incorporate prior knowledge in a theoretically sound way, including trusting real samples more than prior information. And so this is, we don't want to, there are ways you can make Bayesian models kind of less effective. We can do, direct observations, or we can use sort of statistical observations, and of course, real world observations are better. And then 3, it takes into account the acquisition noise. So Bayesian optimization is the current method of choice for optimizing the hyperparameters of neural networks, because evaluating the learning abilities of a neural network is both noisy and time intensive. So Bayesian optimization, they're making a case for this. On the downside, Bayesian optimization has a relatively high computational cost. So searching very large search spaces with this method is not necessarily going to work out. There's a sort of a costly nonlinear optimizer that's required for this. Bayesian optimization trades data with computation, which makes it data efficient but computationally costly. So when we're dealing with these very large search spaces, we need to be able to find a method that searches the search space in the way we need. Sometimes if we're dealing with a tensegrity structure that has some sort of behavior associated with it, we might optimize the tensegrity structure first. It could be the static aspects, it could be the dynamic aspects, and then optimize the behavior, or optimize for the static form and then the dynamic form. We can split our problem up in that way. And so most black box optimization and direct policy search algorithms, such as policy gradients, could substitute Bayesian optimization as an adaptation algorithm by directly optimizing the reward instead of first modeling it with a Gaussian process. And so this is just all speaking to how to optimize the space. And so as a final point, this is figure 6. This is an untethered version of their tensegrity robot. You notice that we have the components here, the springs, the struts, and the nodes here. And they all kind of are in this configuration. This new robot, still under development, will allow for more interesting dynamical behaviors, such as rolling, as well as complex environments. This could, in principle, allow for completely onboard learning as well. So this is the structure. And again, we have the structure. It needs to be stable statically, dynamically, and then maybe produce behavioral modes which allow it to do things. And this is true of biological tensegrity structures too. We want our tensegrity structures ultimately to do things. We want them to bear loads. We want them to maybe the cells to migrate in different ways and still be stable. So we're not just talking about cells, we're talking about cell sheets, we're talking about organs. There are all sorts of tensegrities in biology.